Tonight we're looking for intervals of numbers such that this function is positive. This is a logarithm function. We want to know all the values of x such that the range of this function is positive. Okay. Now you can write this logarithm truth like this, x greater than 1, or you can write this as 1 to infinity. This is called interval notation. 1 to infinity. This means exactly this. All real numbers such that 1 is strictly greater, such that x is strictly greater than 1. Now, and again, if you don't recall this, folks, this logarithm graph is quite familiar. Any logarithm, this is logarithm base 10, by the way, but the base doesn't make much difference here. Recall that an unshifted logarithm looks like this. Okay, and this 0.10, make that a little more prominent there. This is the 0.10, and this is just the inverse of 10 to the x. 0, 1 is on the graph of 10 to the x. 1, 0 is on the graph of the logarithm function base 10. Okay, so from the graph alone, if you're familiar with this, you can see that everything to the right of 1 is positive. All right, so that's why we actually force f of x greater than 0 happens exactly when this input to the log function, x squared minus 12x minus 44, is greater than 1. Okay, x squared minus 12x minus 44 is our new input. Here, x was our input, and we see that it always has to be greater than 1. We now have a different input, and we have to force it to be greater than 1. Okay, and solve. We solve that, we'll have the solution to the problem. Okay, now, certainly if you subtract 1 from both sides of the inequality, you get this statement right here. You subtract 1 from negative 44, you get minus 45, and of course 0 remains on the right-hand side of the inequality. All right, now this, of course, most of these problems are made to factor nicely. This factors into what? X, looks like x minus 15. We're looking for a pair of numbers whose product is negative 45 and whose sum is negative 12. And so that would be x minus 15 and x plus 3, right? You expand this, you multiply these two binomials and you get what's directly above it. Now the factored form makes it very easy to discern the solutions. There's really just two cases right here. For the plus, this factor would have to be plus, and this factor would have to be plus. But the only way that can happen, okay, and I'll just write it right here. Hopefully this is not getting too crowded. The only way that could happen would be from 15 to infinity. Right, folks? And what this says, this is x greater than 15. If x is greater than 15, you got a positive value here and certainly a positive value here, right? Now, the other way you can have strictly positive is negative times negative, okay? So we'll put a minus here and a minus here. And in a similar fashion, if you're less than negative 3, this is sometimes called a disjunction. So you have minus infinity to minus 3 here. And the union of those two sets would be our solution words. I'll just circle this. The union of these two sets would be the solution to the equation. So those are the two intervals that are the solution. Now, you may be wondering what this looks like. Well, it would just be basically two. Let's see if we could sketch a graph here. We'll say that 3 is right here, right? We'll call this negative 3. Okay, so you would have something like this happening. You would have to have a vertical asymptote at negative 2. Okay, it's for the same reasons the original graph looks the way it does. So you'd have something like this. It's positive and positive and positive until it gets to negative 3, right? It's equal to 0, and then it does this asymptotic sort of thing here, all right? And the very same thing for 15, all right? And again, this is a crude graph, but it's close enough. Okay, so the graph would pass through 15, okay, have a vertical asymptote at 14, and look something like this. Okay, folks? So that's the picture of it. It's not necessary to draw the graph to get the to write down the solution, but that's about what it would look like, just the graph of the logarithm of this particular function being above the x-axis once you're to the left of -3 and once you're to the right of 15. But anyway, that is the solution, and thank you for viewing.